Hello friends, welcome back to Electromagnetic Field Theory. We are in chapter number 4, Energy and Potential. Up till now in this chapter, we have gone through the concepts like energy expended in moving a point charge in the electric field of certain another source charge, which also called as work done. On this concept, we have solved 3 problems. After that, we have gone through the concept of what exactly the potential difference is. Absolute potential, we term that potential to be the electric scalar potential. Afterwards, we have gone through the concept of potential gradient. The gradient, what we exactly learned in chapter number 1, we had the representation with the del operator, vector spatial differential operator. We have solved the problems using the formulae of gradient in Cartesian coordinate system, in cylindrical coordinate system, and in spherical coordinate system. Now we have the concept electric dipole. Now to read the term electric dipole, as we are in electrostatic, the electric is okay. After that, what is dipole? So di means two and pole we have. So two kinds of polarities that are closely spaced, so that is called as dipole. So more specifically, we will first of all draw the diagram what exactly the electric dipole is, and will analyze the effect of this electric dipole at the field point. Because generally in electric field there is something, a charge, it may be having a point charge form, it may be having a uniform distribution over a line, uniform distribution over a surface, uniform distribution over a volume, uniform distribution over a certain ring or a disc or a hollow disc. Okay, so for the electric field, because of certain source charges, we analyze the effect onto the field point. Okay, so here also we will be having a certain source of charge and the field point. Now the source of charge will be a pair of two oppositely charged having the same magnitude point charges. So let us see. So for diagram purpose, we take the help of 3 axes: Z axis, Y axis here, and X axis. So we know that X axis in positive, Y axis in positive, Z axis in positive. We have this representation, the intersecting in the origin O. Okay. Now for electric dipole, the definition can be done. Dipole is the name given to pair of charges. Okay, it is a pair of two charges of equal magnitudes but opposite signs. They are separated by a very small distance. Here we will denote it by small d. Okay, and which is very small as compared to the distance between the source charge pair and the field point, what we generally take to be small r. Okay, so distance from the field point to the source charges we have to take from the center of the pair of charges. So as we take a d to be the distance of separation between these 2 point charges, we say there are 2 charges, positive q and negative q. Positive q is at 0, 0, d by 2. So 0 units on x axis, 0 unit on y axis, and d by 2 units onto the z axis. Okay, so here should be the plus q. So q is in coulombs. Now we have to plot minus q. So minus q is supposed to have the location 0, 0, minus d by 2. So 0 units on x axis, 0 unit on y axis, and minus d by 2 on z axis. So here it is minus q. I put the location 0, 0, minus d by 2. Here also 0, 0, positive d by 2. So with d by 2 and minus d by 2, for plus q and minus q, the distance of separation from this point to this point, it will be simply d. Okay, so d is the distance of separation between two charges. They have same magnitude but opposite polarity, and d distance of separation. So what is r? For r we have to consider a field point into the space. let us say this is point P, and the distance R is the center of this pair. So what we have considered here to be the origin. So this is the distance R. Generally we take the vector from source charge to field point going outward. So R AR cap we can say. Okay, so here we have the pair of charges, and from the center we have R. Now the lines joining the first charge and second charge to the point P also we have to consider. So here I can draw a line joining plus Q charge to the field point P, then minus Q charge to the field point P. So here we can give the representations capital R1, capital R2. So capital R1 from plus Q to point P, capital R2 from minus Q to point P, and small r I rewrite it here from origin O, which is center of this pair, to the point P. Now in this chapter energy and potential, we have gone through the concept of electric scalar potential. We have measured the electric scalar potential at the field point. So field point location we have taken this one. So as we have pair of charges, there must be certain potential, let us say V1 because of plus Q charge. There must be another potential effect V2 because of minus Q charge also. So the net or effective potential at the field point P because of this pair of charge, okay, we shall be writing. So here I mentioned D, a distance of separation. Okay, so marking here. So I rewrite here capital V to be the potential. So because of the positive Q charge, we will be writing Q upon 4 pi epsilon 0 capital R1. Capital R1 is the distance of separation from positive Q to field point P. We have to add the potential because of negative Q also. So I put negative sign here, Q upon 4 pi epsilon 0 capital R2. Okay, so here the addition of the potential due to positive Q charge and potential due to negative Q charge we have done. So it will be like this. Now Q upon 4 pi epsilon 0 is common, but R1 and R2 are different. Okay, R1 and R2 are the distances joining the positive Q and negative Q with the potential at field point P. Though they are approximately having same length, but a small difference is there. So the formula for V can be rewritten as Q upon 4 pi epsilon 0 taken outside as constant. In the bracket we have R2 minus R1 upon R1 into R2, and as this is potential I must be writing the unit in terms of volts. So this can be the generalized expression for potential due to electric dipole. Practically the electric dipole occurs at atomic level. Hence the distance of separation from positive Q and negative Q is very small as compared to the distance from the charges to the field point P. So here I have redrawn the diagram. This is R1, this is R2, and this is small r. Okay, and this is the distance of separation between positive Q and negative Q. So just now we have added the potentials at field point P due to positive charge and negative charge. We got this expression. So this potential V is dependent on R2 minus R1 difference and R1 into R2, the product. Now because of the comparison of distance D with R1, R and R2, approximately we can write R1 approximately equal to R2 approximated to small r. Also the product implies R1 into R2, that is nothing but R square. So with these changes, okay, for the diagram we take the help of one angle. So the angle made by the direction going from negative charge to the positive charge, let us say towards positive Z, and the segment joining the center of this dipole with the field point to be theta here. So in that case we can take the difference, that is R1 minus R2 approximated to small d cosine of theta. So for the denominator of that expression we will be using R square, and for the numerator we will be using d cos theta. So in place of R2 minus R1 we will be using d cos theta, and R1 R2 the product we will be using R square. So further we can generalize it. V is equal to Q into d cos theta upon 4 pi epsilon 0 R square, and the unit will be in volts. So this is the generalized expression for potential at the field point P due to the pair of charges, what we say electric dipole. Now if we know the potential in the last topic, that is potential gradient, we have the relation with electric field intensity vector capital E bar. Okay, so finding the electric field intensity at the field point due to this pair of charges, what we say electric dipole, we will be using the relation capital E bar is equal to minus gradient V, that means minus potential gradient. Now here we will be using the location of the point P, field point P, in terms of spherical coordinates r, theta, phi. That is why we will be using the gradient formula in spherical coordinate system. So it will be given by minus in bracket, minus outside bracket. In bracket we have del V by del R AR cap plus 1 by R del V by del theta A theta cap plus 1 upon R sin theta del V by del phi A phi cap. Now we have the expression of capital V, that is potential at the point P due to the electric dipole. So we will be using it. So minus outside the bracket, and for the first term we have the partial differentiation of V with respect to R. So we shall be writing del R in again bracket Q into d cos theta upon 4 pi epsilon 0 R square, bracket complete, AR cap. So this will be the first term. For the second term we have 1 by R and partial differentiation of V with respect to theta. So here we make 1 by R del theta of QD cos theta upon 4 pi epsilon 0 R square, bracket complete, A theta cap. Similarly the third term will be 1 upon R sin theta, 1 upon R sin theta del phi of QD cos theta upon 4 pi epsilon 0 R square A phi cap. Okay, so we get the electric field intensity in this form. We take the partial differentiation and make it more simplified. Hence we get capital E bar electric field intensity vector is equal to minus in bracket the first term minus Q d cos theta upon 2 pi epsilon 0 R cube AR cap plus the second term will be QD minus sin theta, as it was the partial differentiation with respect to theta. In the denominator we have 4 pi epsilon 0 R cube, and this will be along with the unit vector A theta cap. Hence we write electric field intensity E bar is equal to QD upon 4 pi epsilon 0 R cube to be the constant outside the bracket. In the bracket we have twice cos theta AR cap plus sin theta A theta cap, sin theta A theta cap, bracket complete. As electric field intensity we measure either in newtons per coulomb, which is force upon charge, or we give the generalized unit in SI system, volts per meter. So this is the expression for electric field intensity due to the electric dipole. Now, electric dipole we have just now learned. If the pair of charges are situated on, let us say, this line, so here it is minus q and here it is plus q. Okay, so at point, let us say capital P1, okay, which is equidistant from point q minus q and plus q, so we have the lines joining the P1 to these charges to have same length. So I join them, minus q to P1 plus q to P1. So let us say this is R1, this is R2. If this is equidistant, these are having same length. Similarly, if you take another point which is also equidistant from positive q and negative q, so I have to say this is R1 dash, this is R2 dash, they also have same length for point P2. Now if we collect all such points that are equidistant from the two pair charges, so it is a plane intersecting the middle, intersecting the center of the pair of charges of the electric dipole. So we get that plane to be having the same kind of potential, because the potential depends on the distance of separation from the source charge to the field point. So we can say this plane to be the equipotential surface, So here, because of plus q and minus q, the net potential V will be equal to 0. So for electric dipole, we have seen the expression for potential at the field point P because of this pair of charges, that is electric dipole. Also we have gone through the simple expression for electric field intensity represented by capital E bar at the field point again P because of this pair of charges. We have also discussed about the equipotential surface which passes through the center of this electric dipole. It means the pair of electric charges separated by small distance, by distance d, so the equipotential surfaces passes from it. Now one more term we have to discuss about the electric dipole. That term is called as dipole moment. Practically, the electric dipole occurs at atomic levels. So at atomic levels, in the exact definition of magnitude of the charges, the separation between them cannot be done. Hence, thereupon we define the term dipole moment. Now, the dipole moment is actually the product of magnitude of the charges and the separation between them. Hence, it is defined at the center of the dipole. So for the diagram purpose, we draw this line where the two charges positive q and negative q are situated. Somewhere here we take the field point, we again the join positive and negative charges to field point P, represent them R1, R2. This is the center of electric dipole, and here we are going to define the term dipole moment. Now in earlier diagram we have denoted the line joining point P with that of the center of the dipole, that is R, and have used the angle theta. So this is the angle theta, which is angle between the line going from minus q to plus q and the segment R. Okay, so here depending on theta, the dipole moment should be a directional, hence the dipole moment I say it is a vector. So as per the definition, it is the product of magnitude of the charges and the separation distance d. Hence as per the definition of electric dipole moment, we can say it is the product of magnitude of the charges and the distance of separation. So simply we can write small p for dipole moment is equal to capital Q into smaller d. Capital Q is the magnitude and small d is the distance of separation. Now we have also discussed that the potential because of the electric dipole depends on the angle theta. Theta is the angle between the two sides. One side for minus charge to plus charge going, and another is the line joining the center of the dipole with the field point. Hence we have to consider the direction here. So I make d bar here and dipole moment p bar here. So dipole moment is given as p bar is equal to q into d bar, as q is measured in coulombs and d in distance, that is length. So here we put the unit coulomb meter. So this is for the dipole moment. Now using this formula for dipole moment, V, what initially we used to represent QD cosine of theta upon 4 pi epsilon 0 r square, we use the dipole moment representation here. So V will be P bar dot of AR cap upon 4 pi epsilon 0 r square in terms of volts. So using the concept of dipole moment, here we have dot product of dipole moment P bar with AR cap. AR cap is the unit vector going from center of the dipole towards the field point P. So here we take the dot product and in the denominator we have the same. So QD cos theta we have got replaced with P bar dot of AR cap. So this was dipole, electric dipole and dipole moment. Based on to the concept, in the next video we are going to solve certain problems. Thank you.